Okay, what we did in class yesterday, we started beam business, beam elements. And we had a problem which looked like this and solved it maybe a week ago, maybe exactly a week ago, which was a clamp of this type. The cross section is square, it can be a rectangle, but we made a square here. And the top, there is a hole in it, which is entirely clamped. Okay? The face of it is entirely clamped. And then I took the other edge, that bottom edge, and moved it down by 0.01 inch or something like that. And we modeled this thing with solid elements. Okay? And now, if you're talking about the force needed to move this thing down, the stress, well, not the stress, the force needed to move this thing down, etc., you don't have to use solid elements. Okay? You can use beam elements, but at a cost. The cost is you can model that thing on the top. That hole on the top cannot be modeled. So basically, you draw a wireframe like this, either in a sketch or in space, and we're going to do both of them today, okay? And you're going to declare the cross section to be whatever it is. That top point, right point, point 1 is clamped as a beam element, and the bottom point, that's point 0.5 or 0.5, the one at the very bottom, is being pulled down, okay? Now, I want to remind you that CATIA's FEA package does not give information on the stresses in a beam. The only piece that it gives is kind of useless. Okay, it gives actual stress, principal stress, that's totally useless for us. The reason is that when you talk about beams and stress in them, you have to tell me where in the beam. Is it this location, top fiber, bottom fiber, neutral fiber? So to get a plot for you, it's kind of become meaningless perhaps. Some other software do it, but then they decide where they're plotting the stresses, the contour of a stressor or anything like that. Of course, even there you can set those things, but CATIA won't let you do that, bottom line. Now, that does not mean that beam elements are useless, okay? In many situations, you may not be interested in the stress in the beam, but you want to make sure that beams support other things, such as this safety glass. Like what we may be interested in the shield itself, and these are supports. We just have to make sure that they're reinforced properly, etc. Hopefully, this was designed so that it carries that weight, etc. So we are not necessarily interested in the stresses in this, but we are interested in the stresses in this or the bottom, the legs, etc. It doesn't mean it's useless. Okay. Now, the other thing is that people do. How many people are doing mini Baja or Formula One? Are you interested in it, or you may get involved in this capsule next year? Anybody doing it? All right, sir. So what people do is uh, they used to, at least it's perhaps less now because they know a little bit about it. They get involved in the mini-ball project, and the only thing that they have to do is to model the frame. There are some guidelines that it has to meet, as far as the twisting moment, and twisting flexibility, and things like that, torsional rigidity, and things like that. So what they do is they have to give something nice, colorful numbers. So they go and take the frame, which is tubes, metal tubes, aluminum or steel, which is thickness of 1 millimeter, 2 millimeters, 3 millimeters, and then the length of it is that much, and they measure with solid elements because it's so easy to do. Okay? And they get these stresses which are totally garbage, the deflection that are maybe garbage. So the frame does not have to be done for rigidity and for deflection and things like that. Should not be done with solid elements. It can be done with beam elements. Okay. Now, if you want a specific information at the joint where these things are welded together, what people do is it doesn't happen at that level. But what they do is they do a frame analysis with beams. They recover the forces, and then they take that piece where it's welded together, pieces are welded together, and apply those forces that come from a beam analysis to that location and measure solid elements, etc. Okay, let's move on. All right, I'm going to solve this problem first as a sketch, like yesterday. Okay? Are there any questions, first of all? All right, good. So let me go ahead. Dimensions. Just remind me, what is this thing? This is 3 and then 1. 3, 1. Okay, 3, 1. Please, if you have, you don't have it. Okay, so we'll look at it. Let's start with the part design. Although at some point I will have to go to the generative shape design because I have to join stuff. Okay, I have to join stuff. We'll go there. Oh my God, runtime exception. This was running from yesterday. Maybe that's what happened. You get runtime exception error. There is nothing you can do. You're doomed, basically. So let's wait for this thing to pop up. Okay, good. Usually doesn't happen like this, but this Katia was running since yesterday on this, so who knows? I brought my C clamp here because I want to talk about it later on. Okay. So first of all, I'm gonna get out of the product, start with the parts file, and right away I'm gonna save it. So file, save management, save as, desktop, new folder, I'll call it C clamp, sketch. C clamp, sketch. Okay. Uh, yeah. Good. I just happen to be in the wireframe and surface design, but it really doesn't matter. I can draw it anywhere. So on this plane, vertical plane, I will sketch. That's C, and I don't have to be very accurate. I mean, we can clean it up later, something like this, like that, and that's it. Except that it's not. I want to make sure it's symmetric. Just feel better. That's all. Not in this. There are no planar symmetry in this problem. And we'll talk about that in a minute, why there are no planes of symmetry. Because the top is clamped, the bottom you do something else to it, okay? The shape is symmetric, but the top is clamped, top right corner is clamped, and the bottom is not. If I was applying that force on both sides to move this thing by 0.01 up, 0.01 down, yes, this is a plane of symmetry, and we're going to worry about it, but not the present model. Okay, clean it up. So this guy, constraint using dialog box, you make it symmetric. Very good. And I'm going to put some dimensions here just so that it looks similar to what we had before. This, I think, is 3 inches. 3 inches. Okay, so that one, control this point, coincident. Let me see if we can make it coincident. If not, do something else. Cancel. Just dimension it. Dimension. Where's the dimension? Okay, good. Now, exit. Exit. There may be some other dimensions here. I don't know. I'll just leave it the way it is. Okay, so I'll just leave it as it is. Now, this is the part. And because the cross section is not a circle, I need a reference point. I need a point, orientation point. Okay, and orientation point, I will make it, for example, just 0, 0, 0. How about that? So I need a point here, point. coordinate 0, 0, 0, not on a curve, coordinate 0, 0, 0, right there. It just happens to be right at the origin. The way the orientation point works is that from that point, you drop a perpendicular to the curve. For example, the bottom edge of the top edge, or the circle. You drop a perpendicular. That is your y-axis. X is along the beam, and Z is perpendicular to both of them. Knowing this does that remove that uncertainty and randomness out of it. Okay. In this case, the only restriction is that this point cannot be on this curve or on the continuation of it. Because if you drop a perpendicular from that point to the curve that it sits on it, you're going to have a problem. That's the only restriction. Exit. Join. If you don't join, there's nothing you can do with the rest of the problem. So I'm going to join it. Select the sketch. Good. Material. Apply material. The order is not important. The order, which one you do first, join or the other one. I'll make it out of steel on that piece. Okay, that's it. As far as the model goes, this is it. If I was applying 0.01 displacement up, 0.01 displacement down, which is a different problem, on the test, you'll have to take half of this because there's a plane of symmetry, but not in this problem. And the other thing is that do not solve this problem with solid elements, because on the test, we may be giving you drawings like this and say, model this problem with beam elements. Use the most appropriate, we tell you. Then don't look at this and say, hey, here's a solid, so I'm going to do it with solid elements. You have to use beam elements with this problem. Or we will tell you that. Okay, sometimes we will tell you, sometimes we don't. Because if I drew this thing like that, you will say, hey, I know it's a beam, but this is kind of bulky. You might say, you know, and there's a hole there. You can't do it with beams, etc. Okay, so now we're going to go to generative structure analysis. Nothing fancy here, you know, no point that I want to put it on there. It's just straightforward beam. And say OK. Here's the beam measure right there. You click on it, you select it, turns yellow, that's good news. If you have not joined, you could not do this anymore. Okay? And I'll use 0.2 inch point. Say OK. Now we're going to do, now that we have defined the geometry and meshed it, we're going to do the section, cross section. Okay? 3D, no. 2D property, no, that's for shell. 1D property for beam, it shows you an I-beam. So you click on it. It says, what is the cross section? Well, first of all, what is the support? The support is this. And the reason I put a circle there, because yesterday when we worked on it, it was a circle. So we go change that thing to rectangle. And the reason it doesn't show a rectangle, because the dimensions of the rectangle are 0 and 0. So now we're going to put that 1 and 1. At our problem, it was 1 and 1. This cross section was 1 and 1. So 1 here and 1 there. You say OK. Notice that I cannot close this. I cannot close it. OK is dead because it's waiting for you to pick the orientation. So I'm going to click on the orientation and select this. I know it's going to work because look, that's the way I wanted it. Right? I thought about it. We thought about it. Okay. And then we say OK. Let's save our analysis. File, save management, analysis, save as. I'm going to put it in that same folder because I'm going to put all these in different folders. It's okay, no problem. All right. The top is clamped, so get the clamp thingy. Okay, and the bottom is being pushed down by some amount. By the way, let me remind you, beams, each node has 6 degrees of freedom. So when I say clamp, that means that point does not translate in direction X, Y, Z, okay, and does not rotate in any other direction. So you could have done, for example, if you wanted to use a defined restraint, check all 6 of them. You could have done, that would have done the same thing. Now we want to take this end and pull it down. We have gone through this thing last week. We remember. First, you have to make it 0 down. Go 0 down. 0 inches down. And then you can change it. So here is the user-defined restraint. This bottom point moved in the direction Z by amount 0. Okay. And now we can go and change it. Go to load toolbar. There's enforced displacement here. You select the thing that you did. I mean, if you're having a hard time, go to the tree. But I just picked it, okay? And say downward minus 0.01. And then we say okay, and save, and run. So, yeah. Nothing fancy. It's going to look like that. Let's put it in the front view here. Front view. Right, so you can animate it. Okay, that's the way it should be. You want numbers now? That's a different story. Plot the displacements. You get 0.01 inches. Now, these are all in the form of arrows. See, these are arrows. And notice that they're tilted because this thing not only goes down, it also goes to the left, for example. Okay? It doesn't come out of the plane, but it goes to the left. So if you want color, nice colorful thing, double click on this, either here or the tree, average ISO, and there. Okay? You want the stresses, tough luck. Okay, you can plot the stresses, but the principal stress, which is axial stress, and that's the only thing you get, you don't get anything useful out of. How much force do I need? Does anybody remember what the process was? Yes? Yes, you put a sensor there and then update it. Now remember, on the test, if you need information like this, write it down. Remember, open book, open notes, no internet, no YouTube, no videos, etc., no cell phone. So write those things down, okay? Because you don't have access to internet. You will not have access. Okay, so we go here, right-click on the sensor, right-click, create resultant sensor, reaction sensor. It says, where do you want it? You want to put it up there? Or do you want to put it on the restraint that you put? It's going to give you the same value. It's going to give you the same value. So for me, it's easier to select this because it's right. Otherwise, I have to go here and find out where that restraint is that I did is right there. Okay? And then update. And you get 243 pounds. 243 pounds. Remember, when we did this problem last week, we used solid elements and we cut through it, I think. We cut through it half. And then we multiplied this thing by 2. Because whatever we did was only half of the C file. Okay? Here though, this is it. This is it. And remember, do not say cancel, because if you say cancel, there is no record of how you got this number for us. Okay? Say okay. Write it down on the paper if we left the box for you to write the answer. And then, because we know how you got that number, it's there. I can double click on it and see where you got your 243 from. Okay, don't say cancel because cancel would have eliminated any record of that. Any questions here? Yes.
Can you share yourself quickly just doing this answer again?
Okay.
Down for 1 second.
All right. Okay, so let's do another one because you can create as many sensors as you want. You put the cursor there on the sensor, right click, create resultant sensor, reaction sensor, okay? And it says where? Last time I took the one down here, now I'm going to take the clamp. How about to convince you that actually it's going to give you the same value? Where's the clamp? Right here. This one is for the clamp, okay? And update, I should get almost 243 or very close to it. 243.
So for the first time you selected the user defined?
Yes. Because these are not always exactly the same for different reasons. Okay, so let's go and repeat the same problem using wireframe. not sketch, because I've never done a problem like that for you. Okay, so let's kill this thing. I'm going to start fresh. Okay, so I'm not going to even bother doing this thing. Let's start with another part file. Immediately save it. So file, save management, save as, desktop, not here, not here, because I don't want to mix these up, because one of your friends asked about cutting things like that. Say put it in a separate folder if you want, so that you don't mess it up. So up, one level up, new folder. Instead of sketch, I call it wireframe. Wireframe. I think C-clamp wireframe. How about that? C-clamp wireframe. Okay, good. Goes there, and here. So I'm going to create, how many points in space? I'm going to create, let me see, 4 points in space like that, with coordinates that I give it, and then I draw my line and circle, etc., etc. So let's go ahead. I'll make my own dimensions, okay? So because otherwise I have to type these coordinates in, okay, whatever they are. So let me go back here. I'm going to create five points. And I know the coordinates. What is that? The x is 0. It's just the y and z that I have to give. For example, the one on the top left corner, I'll make it y of I don't know, y of 4, okay, and z of I don't know, maybe also 4. That's my first point up there. Then I do one on the left of it, so another one. This one is going to be y of 0. How about y of 0? There, same z, of course. Another one. Let me double click it this time so that I don't have to go. How about down here? Let's do the ones down there. The only difference is that the z is negative. So this one is negative. It's right there. Why is it closing this? I don't know. And then the y is going to be 4. And one on the left for the apex of that circle. So for the other one, that will be z of 0, and obviously y of 4. It must be y of 4. Where do you go? Oh, minus 4. Minus. Okay, so I have my five points in space. Now I'm going to draw my lines. Here's a line from here to here. Okay, another line from here to here. Okay, and then a circle. Must be somewhere. Here's a circle. There are different ways of making a circle. You have to read this thing carefully. It says, first of all, circle type. Well, I have 3 points. I can use 3 points, for example. Let's change this thing to 3 points. 3 points. It says, well, pick the points. So there is 1, and there is 2, and there is 3. I think that's pretty much it. There. Now, let me not join these. I'll have to come back and join it. Or we have to do more work. So let me not join it, because I want to show you what will happen. We'll come back and join it. Apply material to it. We can always join later. There's no problem. So apply material to it. Before I do that, my cross section also is rectangular or square, so I need an orientation point. And I cannot use any one of these because these sit on the curve. So let's do another orientation point at corner 0, 0, 0. Yeah, right there. Okay, good. Material. I keep losing this guy. Material, metal, steel, underpart. Say okay, and save. So now we're going to go to generative structure analysis. I'm not going to even save this because I have to go back and join it and then come back and clean it up. So we say okay. Now, when I try to mesh, you see that? Mesh? It won't take the whole thing. It'll do it one at a time. Because it's doing one at a time, at these points where they come together, where the curve and the line come together, they're separate nodes. If they're separate nodes, they don't even know they have to move with each other. It is possible to fix that, but you can see why joining would clean this up. Okay? It is possible to do things where the separate nodes come together, and we will do that. But right now, don't worry about it. Let's go join it. You see what the issue is? And even if you want to put cross-section on it, they can be different, completely different. A circle, a rectangle, because these are all separately meshed. Okay? So cancel that. Cancel that. I will go back to my part, which is sitting in the background, and join it. Select all of these things. It's not a sketch anymore. It's three different curves. Okay, three different curves. So I have to select them. Notice that. Notice that I did select three curves. When it was a sketch, as soon as I picked the sketch, the whole thing was done. Say okay. No problem. Let's go back to our analysis. Now, when I go and mesh, the whole thing is going to be done at the same time. And there won't be any different nodes at the same location anymore. They will move together. Say fine. We can do the section. It's the same information as before, but because we join it, it's going to do it for us at the same time. Orientation point, we selected this point. I do that. Notice it's turned it around. It looks nice and okay. Now, clamp. Do not put it on that point. It will put it for you, but it doesn't understand. See, when I select this thing, look at what it says at the support in the box. It says 1 point. Point is not a geometrical, it's not a finite element entity, it's a geometrical entity. So it'll take it, but when you run it, it doesn't see that. So what I do is I will, first of all, remove it, hide these points that were entirely geometrical in nature. I just need to hide these two, that's all. The other ones are not going to come into the picture anyways. So clamp this, notice it doesn't say point anymore, it says one vertex. That's different. Okay? And same story as before, you apply a restraint to this bottom vertex in the Z direction because you can change it. Same stuff here, so that's this. Good. And we're going to run it. Hopefully we didn't forget anything. I don't think we have. And displacement. There we are. Okay. Now you might ask yourself, and we did talk about this thing yesterday a little bit. You might say that, okay, well, why do I bother doing this thing? It took more work trying to put these points and lines and things like that. Can I not put it in the sketch? The answer is yes. But if your curve is not fitting in a sketch, meaning fitting in a plane, you can't put it in a sketch. If the curve looks, if the geometry in the space looks like this, there's no way you can put this in a sketch. You have to do it as separate entities, splines or lines, etc. Any questions here? Now, I want to repeat the same problem, except that instead of clamping this and pulling it, I'm going to pull it both ways by 0.01 inch. This is going to be a plane stitch. Okay? So, save this. I said I was not going to save it, but why not? File, save management. Every time I said let's not do it, I needed it a few minutes later. Not in the wireframe. Yeah, that's good in the wireframe. Okay, so the next one I'm going to do it as a sketch. As a sketch instead of doing this. Okay, so get rid of this. Again, ignoring dimensions. Part. Okay, on this plane, I will sketch my half of my C clamp, right? Like this. I mean, you can draw it any way you want. You have to clean it up. That's as simple as that. So I'll do it right first time. Okay, this is also not cleaned up. Look at where the center is. It's not on that line. So I can select this, control that, make him coincident. Okay, now it's right. Ignoring dimensions. I'm not going to bother doing the bottom piece. You can if you want. Basically, you should mesh it later on. Okay. Okay, exit. Join it. Join. Uh, join. Apply material. Apply material. Make it out of steel, metal, steel on the part. Okay. I used to get very. No, wait a minute. This is recording, so I'm not going to say it. uh, let's see now. This is it, right? A coordinate. The orientation point. I need the orientation point. All right. We applied our material. We joined. Save file. Save management. File. Save management. One level up. New folder. C clamp. C clamp symmetry. But remember, this is not the same problem that we did a minute ago. These are different problems now. Okay. Where is the C clamp? All right. This is going to be very important. I want you to pay attention to it. Even those people who are talking back there, they're doing their own stuff. That's okay, no problem. So you go to generative structure analysis, mesh it, put section on it. Okay, first of all, the support is this, and the orientation point is that, and we pretend the dimensions are correct. They are 1 and 1. Good. Okay. So this point is a plane of on a plane of symmetry. Look. Yeah. On this plane of symmetry. This plane of symmetry. Let's pretend that up is Z. What can you tell me immediately? Up is Z. So this is XY plane. This is XY plane. Up is Z. What can you tell me about displacement that you know? What? But I mean, displacement where? In what direction? You're right. Z. Very good. So let me show it to you a different way. The person who's standing on that location does not see that point underneath the foot going up or down in the Z direction. Okay. The displacement normal to the plane of symmetry is 0. So displacement in Z is 0. So let's go to this table. XY is a plane of symmetry. Displacement in Z is 0. These two guys are free, but you also have to do the rotation. Rotation is exactly the opposite. So if this was free and this was free, this is 0 and this is 0. If this was 0, displacement was 0, rotation is free. Very frequently, people don't do all of these, and we don't give any part marks. You have to do it right. You have to do it for beams. You have to do all of them to get full mark for that particular portion of the problem. Okay? So let's go ahead and do that. User-defined restraint. Let's clean this up so that we start fresh right there. No displacement in direction Z. Rotation opposite. So if this is checked, this must be free. If these are free, you can see they are free. These must be checked. No part marks for that portion. Okay. Let me give you an idea. If this problem was given to you, I would say 20 marks. Be, having correct restraint would be what 4 marks? No part marks. Okay. Now the rest of it is the same. So you apply a restraint up at this location. Only displacement in the direction Z. Now it could be in a particular problem you do it a way you didn't recognize the issue, but you did something that happens to be okay. It does not affect your work. Okay, then we are flexible. Okay, so I'm saying that if you did something that is correct but for the wrong reason, I pretend that you know what you're doing. All right, and then you give it an upward displacement. Of course, plus, right? I'm pushing it like that, doing it like this. So I change the minus to plus and run it. Ah, okay, so we're gonna figure out what's going on here. Yeah. Okay. Obviously, your worst enemy popped up, and we thought we did everything correctly, but maybe there's something that we haven't looked at. Now, look at what I did there. What I did there, I followed the symmetry rule. That is correct. That is correct. That was correct. Rotation about Z was free. Displacement was 0. Rotation was free. You followed the correct process. But because of the nature of the problem, if rotation about Z is actually free, then this can go like that. It has nothing to do with the symmetry. The symmetry we did it right. But because displacement, rotation about Z is actually free, it can actually move as a turn as a rigid body like this. Okay, and you can see that actually. If you look at this, it will see that right there. You can see that it pivots about that. You won't lose mark for symmetry. The symmetry is correct, but you can't finish the problem. You didn't finish the problem because you didn't know what to do. You lose marks on that side. Your symmetry was okay, no problem. So we're going to have to fix that, prevent that rigid body motion. There are other alternatives. You can probably take one point, say, don't come out of the plane. No displacement in the direction X, for example. You can do that. As long as you can make it work, no problem. But the easiest way to do it is just actually that rotation 0. If you don't like that, go fix one point, not move in the X direction. That's all. Move, not move, not move, not, I don't mean rotate, okay? Not move. Either way, so deactivate that. As a matter of fact, let me try it. Let me try it. Deactivate this thing. Okay, let's go and try one point. For example, you have to take this point because this point doesn't go anywhere. Yeah, this point is, we can also fix that point, doesn't matter. Let me just try this one. User defined, right there, user defined. This point, no displacement in the direction X. That bottom point can move though. That bottom point can actually move. Okay, that's the problem. This is not going to do it. This is not going to do it because this point can in fact move in that plane because of the symmetry that we put in there. So let's also do the following. This cannot move for sure, but this is not going to run. We'll fix it because on the test you have to do these. Right, because this guy is going to be moving. So I'm going to select that point. It was okay. If I'm having a hard time, hide these guys, hide these restraints. This point does not move in the direction X and Y. And think about it, it makes sense. Compared to this person, this point should not go in the direction X and Y. Okay? Let's try that. I'm pretty sure this is going to work. Okay. There are other ways of doing it, or just whoa, 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 what's going on here? Let's see. Let me see a deflection here. That rotation must be fixed also. This did not. This did not do the job. This one did. Oh, wait a minute. Wait, yeah, this one did not do the job. Oh yeah. Direction. What did I say? Direction Y should have been X. It should not come out of the plane. It should not come out of the plane. It should not go in the direction X, direction 1. Let's try it now. I just checked the wrong box. Would have been okay, yeah, right there. And the reason it looks like that because you set the scale. There we are, and it goes up. You can see that it goes up. It's supposed to go up. Animate. Yeah. If you look at the front view, it goes up. Okay. There were different ways of doing it. Yes.
So the mistake for the one point you were saying it wouldn't be able to travel in the y direction?
By mistake, this point, to prevent doing this, I put the restraint in this direction. I said, don't go that way.
So when you bend it up, it'll go into the y direction. That's why you can't.
Hang in there. This last one that did not run was because I tried to say, don't come out.
Yeah.
But instead of saying, don't come out, I said, don't go this way.
Right.
And it does go out. It does go out. If you in now it does. Now it's correct. But before that, it didn't run. Before that, it didn't run because I meant to say this top point should not go in this direction. Inadvertently, I said should not go in this direction. Now, force. So put the cursor there, right click, create sensor, reaction sensor, and select. It's entirely up to you. You can do the clamp, for example. There is no clamp, but you can use this. Let me see now. What did we do? Oh, that restraint that we made it go up, right? Right there. Update. 53 pounds. So in the box, what do you write? How much force is needed to pull this thing up by 0.01? This way and that way. What do you write as the force? Yes. No. Because just because you took half of it, look, that half doesn't affect the thing. You know, it's just 53 pounds. All right. Let me show you. See, and this is the reason you might say that, well, this is not fair. You know, I get no hard marks for some of these things. The answer is no, because for that particular thing, you have to think about it. The difference is 2 or 1, right? It's a big difference. Okay, so let me do the following. I'm going to save this and then show you your something that you need for your homework. Okay, your homework is not going to be available for another 15 minutes, so don't rush. Save management, analysis, save as, symmetry, good. Okay, so this is going to pop up. You can download at 9:30, quick, very soon. But all right, the problem that I'm going to talk about right now in about 10 minutes, is this problem, one of your homework problems. And notice that It looks like kind of thing that came from maybe a test last year or 2 years ago, 3 years ago, whatever. Use symmetry to reduce the model. Use the most appropriate element. And down here, you see some parts. Now, I don't guarantee that it's going to be split like that, but I can show you roughly, if this problem had 20 marks, I think this is like 25 marks, how it was distributed. I don't guarantee it's going to be the same thing here, but it is. First of all dimensions are correct. Okay. Don't make 1 inch 50 inches. Okay, that's why it has only 1 mark. Correct symmetry taken into account, 5 points. And in many situations, we write no part marks. Okay, we write no part marks. This particular year, we didn't write that. Restraints correct, 8 marks. I will go to the restraints in a second. Okay, and is the load correct, etc. Write your answer in this box. How much force is needed? But the problem was this. As soon as you see this, you should recognize that this must be done with what elements? Beam elements. Some people who are not here, were never here. Okay, so they see this, they say, I'm going to make it like that. And then I'm going to click on the thing, Katia is going to mesh it for me and do the rest of the problem. No, beam problems. Now, this end is clamped and that end is clamped. This clamped, this is clamped. And we take the middle point and push it down by, I don't know, 0.01 inch. First of all, this is this geometry that fits in a sketch. You can draw it in sketch. So it's entirely up to you whether you want to do it in sketch or you want to do it as a bunch of lines. No problem. But then you have to look at it and say, oh, this is being pushed down, so everything is symmetric on the 2 sides. Okay, it is. It is symmetric because this thing pushed down, clamp, this is pushed down. So x, what is that? Xz is a plane of symmetry. No translation in y. As soon as you see xz is a plane of symmetry, no translation in y. And rotation, opposites. Okay, rotations are important here. Now remember, if I took this thing and push it in some other direction, all bets are off. There is no symmetry. If one end was clamped, the other one was not clamped, and I was pushing down, no symmetry. If this diameter was different from this diameter, no symmetry. Okay? Now, if you don't use symmetry, first of all, you lose some marks, but it also tells us that you may not know what to put for the restraint here. Okay? Not only you did not see symmetry, but maybe you saw it, but you did not know what to put as the restraint. Okay? The rule for the restraint, we discussed it. If xz is a plane of symmetry, no translation y, that's easy, rotation, opposite. And that is referring to essentially this table. You don't have to memorize this, it's so obvious. Because people seek translation, rotation is what they generally cannot figure it out. Rotation is the opposite. Now, the other thing is that how much force is needed, you know the process of doing it, put a sensor there, and eventually multiply that by 2. Now you multiply it by 2. Because if you're modeling half of it like this, the force that you get is only for the part that you're modeling. It would not apply to the C problem because it's a different thing. You know, double that. That has to be doubled. Okay? And, now, what if somebody decided not to use symmetry here? Yes, you can lose part marks, whatever they are, for not seeing it, for not telling us whether you know how to use symmetry restraint, but you insisted that I want to do this thing without symmetry. And this point has to go down by 0.01. So can you tell me how are you going to do that? 0.1, that middle point should go down by 0.01. Can you tell me? Yes. That's good. So one way is to, this line don't run like that. Just do a line from here to here and here to here. That's one way. Now, if you didn't want to do that, or if the geometry came to you from Mexico and they didn't give you, they give you solid object, a dumb solid, then you don't have a choice. You may not have a choice in doing this thing, but you can create a point and say, include this point in the mesh. We did that thing yesterday. Include this thing in the mesh, and then you can move that thing down, that node down by 0.01, and then, yeah. So the problem is that the people who don't see that, they take this middle point, they put the mouse cursor at that middle point, and they select it, not realizing that it's the whole thing that is being moved down by 0.01. That's a different animal. It's a different animal. It looks okay, but it's not the same problem. All right, folks. So this is going to be one of your problems. If you want to, want to start, I'll leave it here. You can see it, and then you can download it. Yeah, there's some questions here.
So for this one, you would multiply by 2 because where you're taking the force is where you cut it.
Yes.
And then the other one you did without.
Yeah. Yes, that's a good way of saying it. Yeah, that's a good way of saying it. Yes.
So at that point, you don't want us to move in the X or Y direction, right?
Okay, see, if it's vague, ask us. But all it says here, it moves vertically down. So I leave everything alone, right? It will definitely not move in the direction. It will not move because there is nothing that to make it move in that direction. And it definitely will not move in the y direction anyway because it's symmetry. So although we didn't say it, because of the way things are, if you move this thing down, it cannot go in the direction x anyway. There's no force to put it in direction x.
Yeah. So for your restraint, would you include that in your restraint saying don't go in that?
No, it's not necessary. And even if you did it, that's the one that you get full mark for that because you inadvertently said, maybe I make no displacement in x. That is correct, but you didn't see it because it did not move in that direction. That's okay. Even if you included it, that's okay. All right. So, two problems on your assignment. Just wait for a couple of minutes, 5 minutes. Okay, let's stop this.